Now we're going to work with one of the distributions I used a lot when I was working with analytical instrumentation, and it's called the normal distribution. But don't worry, when it gets to Halloween, we'll go ahead and do the paranormal distribution. You get it? All right. So first of all, let's talk about distributions. If you roll a die 360 times, what do you think the results would look like? Well, if we're doing just one die, all of the outcomes should be equally likely, and there's 6 of them. So I would expect to get 61, 62, 63, 64, 65s, and 66s. The distribution shows the expected outcomes. Now, admittedly, in real life, we know there'll be some variation here, but this is what we theoretically expect because each roll is equally likely. This is called a uniform distribution. Now, that's not the only type of distribution out there. You can roll 2 die 360 times and plot the sums. And if you did a table showing the sums in the different ways to get from 2 to 12, you'd find out that 1/6 of the table will get you 7, so that would be 60. And then 5/36 would get you 6s, and only 1/36 would get you 2s. That's where you roll 2 1s. So 7 is the most likely, and 2 and 12 are the least likely. This one doesn't really have a name. But now we're going to go ahead and talk about some other distributions that have a name. And that is the distributions we'd use for things like SAT scores or heights of people. All of these have sort of what's called a bell curve. And the actual name for it in statistics is a normal distribution. There's a distribution we keep seeing when we work with statistics, and let's take a look at flipping coins. So first of all, if I flip the coin once, I expect to get heads maybe 50% of the time and tails 50% of the time. And you can say one of those is 0 and one of those is 1. If I increase this by 1 to 2 coin flips, then you find out that I would get 0 a quarter of the time, 1 head half the time, and 2 heads a quarter of the time. If I move it up to 3, then you see that it's starting to break up a little bit more. And if I have 4, there it is. And as I add more and more coin flips, you notice the distribution of heads starts to take a shape. And this is a very popular shape in statistics. This is approximating a normal distribution. And here's another picture of it. So when we're working with the normal distribution, we use what's called the 68, 95, 99.7 rule. So about 68% of the data is going to be within 1 standard deviation of the mean. If we were looking at heights of people and the average height was, say, 5'10" for guys, it's not, but we'll pretend it's like 5'9" for guys. All right, you would expect there to be more people in between, say, 6 feet and 5'6", than to be, and there to be less people as you get out here. So you can find out that more than half the people are within 1 standard deviation of the mean. And then if you go out another standard deviation, that gets almost everybody. That gets 95% of the people. And if you go 3 standard deviations, that really gets almost everybody, gets 99.7% of the people. An interesting thing to know, because it's symmetrical, this 68, if I only look from 0 to -1 standard deviations, you'd have 34% in this piece, and you'd have 34% in this piece. 95%, if I split that in half, that is 47.5, and I would subtract that 34% to figure out how much exactly is in this piece. So all of these pieces should add up to 1. So let's go ahead and use the calculator, and I'm going to show you the rule here just with the 1, 2, and 3 standard deviations. So you can do it by hitting second distribution, scroll down to 2 or click on 2, and enter normal CDF. You put your lower z-score, which I said is -1, and we're doing 1, and a comma. And then you do your high z-score, and then hit enter. So you see 68% are within -1 and 1. And if you keep going, we can go -2 to 2. And there's your 95%. It's not exactly 95% or 68% for that matter. And then we can look at 3 standard deviations from -3 to 3. So these are numbers you should actually have memorized. It's called the 68, 95, 99.7 rule. So let's go ahead and take an example with a 1903 study on inheritance, and the average height of mothers was 62.484 inches. This was actually the leading study to help establish the normal distribution. They found out the standard deviation was 2.390 inches. So the way we write the models, we have this n saying that our distribution is approximately normal, and here's the average, and there's the mean. Then we put our mean right there in the center. The question is, what is the interval of heights for 68% of the population? Well, you're supposed to know 68% is within 1 standard deviation on either side. So to find this lower end, I'm going to take this number minus 1 standard deviation, and that gets me 60.094. To find this upper limit, now I add 1 standard deviation to the mean, and I get 64.874. So the interval is 60.094 to 64.874. Okay, now we want to know what percent of heights are less than 67.264 inches. Well, we're going to calculate the z-score. We're going to find out the number of standard deviations that is away. And there's a reason I picked it, because if I go that minus my mean divided by my standard deviation, I get 2. Okay, so 2 standard deviations, that means it's right here. And I'm trying to know what's less. So that's this area over here. Well, your table in the back of your book for normal distributions basically gives you this number. The first column is for easy numbers, where it's up to 1/10 of the standard deviation. And at 2.0, it's 0.9972. And so we know this area here is 0.9972. I'm sorry, 9772. Now, the other thing, if you did it on your calculator, you could do normal CDF -100. Now, you could ask me, where's this -100 coming from? And I'll get to that in a second. And 2, you know where the 2's coming from. That's right there. And I got the same number on my calculator. Why am I going -100? Well, if I go 4, I'm going to be a teensy bit off here if I go -4. So I just go out far enough so that I know there's no way that there's a big number out here. I'm trying to minimize the amount of my error. So you're going to find out I use -100 a lot for the left side, and I'll use +100 for the right side.